hope everyone, saw the video which I was like. I'll take a few minutes to explain, my thoughts. Okay. So I really hope that you saw the video which I sent you in the mail. If not, just look at this. This is Earth. This is a satellite which is rotating in this green axis, okay, around the Earth. If there's some impact, some kind of force that acts for dt moment that gives this satellite a velocity in this downward direction. Okay. So instead of the path becoming like this, the path is the blue one now. Okay, of the satellite. So carefully observe this. Okay. So basically, if it wasn't Earth and if it was a gyroscope spinning, a force, one force for dt moment, it would have changed the axis of the gyroscope like this, the whole axis. And if it was pivoted around this point, it would have changed it like this. Now, if I keep giving this force at every moment, okay, the axis will, start rotating this way. So that's pretty much what gyroscope is about. And basically, if you rotate it this way, you get this system wherein your gravity is causing the this point to move in this velocity, and hence it is rotating. The axis is rotating. So that's what your gyroscope is about. Okay, that's the intuitive feeling. If you haven't watched the video, you can go and watch it. I mean, after the class, of course. So yeah. So basically, I wanted to explain circular motion a bit, and come to this too. Okay, in circular motion, basically, what happens is that there's a force that's pulling in this direction, and it has a velocity in this direction. All right. So before this falls towards Earth, there's a vector in this direction that changes you know the radial force that's been acting. After a while, the force would be in this direction. Okay. So that's the scene over here. So this is circular motion. Okay. At every time t, the vector is changing. The radial vector, the radial force is changing. So if I take it over a period of t by 4, the average vector is in this direction. Okay. So hence in t by 4, the average vector is in this direction, and in t by 4 time period, it caused this vector to reduce and this vector to gain some velocity in this direction. Okay. So basically, if I said there's a circular motion, and if I take one full time period t, the average vector is zero vector. Hence, we can see in time t, this did not change any velocity. That's how I explain circular motion. Similarly, for gyroscope, the intuitive part is that the torque, any movement, any push given to, the torque due to gravity, if there was no spinning in this coin, it would have rotated it like this. Okay, so it would give a velocity like this in this direction. Okay, so but since it is spinning, instead of falling, okay, wait, yeah, hello, yeah, instead of falling, now what's happening is that मतलब इसके गिरने से पहले before it's falling, this point is moving up. You understand that, right? So before that's falling, now that's causing the axis to rotate. Now again watch that video which I recommended to understand this intuitive part. I'll explain you the equivalent part of this again over here. Okay, so the torque here is in this direction, and the angular momentum is in this direction. At t by 4, time period by 4, the angular momentum will be in this direction and torque will be in this direction. Okay, so the average torque is in this direction, which you apply for t by 4, it loses angular momentum from this direction and it gains over here. Similarly, if you take a full circle, the average torque is zero. Okay, it's zero. There's no torque being applied. So in one time period t, do you see the angular momentum changing? No. So that's how I explain it. But then, the intuitive part comes where you need to look in for very small dt time and how it's changing, how the L is changing. Okay. So let's move on to the first question. Okay. So yeah, I'll give you some time to read and tell me if, what to do with this. Okay. This is the z-axis. Okay, I'll explain the question. This is the z-axis. Okay, and this is rotating about this axis with capital omega, and the wheel is also rotating. Okay. Uh, since it says it's pure rolling, okay, it would be rotating in this way. Okay, with omega. So basically, all you need to do is to find the uh, ratio of contact force with respect to the surface of the weight of to the weight to the stone. Okay, there's a force mg acting over here. There's a normal force over here. Now, since you know the setup of gyroscope and you know what needs to be applied, this must be pretty easy to solve. Okay. Uh, okay, I guess I'll begin with the solution because I'm not getting any answers. Okay, so basically we know how gyroscope works, right? And we can see this is a gyroscopic setup. Okay, since you could similarly see this is new to you, so that's why you might have some problems in grasping the concept. But with enough number of questions, you can solve it. Okay, imagine this was a circular motion. Okay, what would you do? You would straight away apply the concepts of circular motion, which is mv square by r. That's the radial force that's acting in this direction, and there's a pseudo force. Okay, so here similarly here, all you need to do is apply this. Okay, all you need to do is apply this. So just a second. Yeah. So basically, change in angular momentum is equal to the torque is equal to omega L. Okay. So basically, there's a force N acting on this point. Okay. There's a force mg acting on the center of mass. Okay. Initially, the angular momentum is in this direction, and omega r is equal to omega b. B is the radius of the wheel, so it's purely rolling. It's given in the question. Okay, and since n is acting in this direction, there must be a force that's acting in the downward direction. Okay, so basically it's causing it to rotate like this. But since it is spinning, it won't rotate like this. The axis will rotate around this point. Okay, around this point, this axis will start rotating, and this L will change at every moment. Okay, so basically L is equal to I omega. So okay, so this is L is equal to I omega. Okay, so which is equal to half mb square. B is the radius of the disk, and I took omega from here, from this relation. I put it in here. Okay. Now I just use this equation. I equated uh, this. Okay. Yeah, this R should come here. Okay, it's torque, right? Yeah, sorry. So yeah, so I equated this with this. Okay. Basically, I equated this with this. Okay, and you can solve it now, right? Just send mg over here, and you have normal is equal to force plus mg. So is there any doubt in this question? See, basically, there's a gyroscopic setup, and just like it's just new. Okay, if you understand the concept, it's all one time. You just need to understand it intuitively one time, and rest you just need to know the concepts. Okay, here the torque is causing the angular momentum to rotate instead of changing the magnitude, and there's okay. So basically, all you need to do is understand that. So so yeah, but physics is a model. Okay, anything that sits with your ideas and with the math, it works. Okay. So my next question to you is that in this question, why can't I just say there's a tension over here, there's a tension over here which is equal to mv square by r, and there's a force n is equal to mg. Why can't I say, and it's rotating with omega r happily? So why can't I say that? Can someone answer me? Like if yes, see, I'm telling you the answer. This is totally wrong. Okay. So now give me the reason. What's not fitting? If anyone of you can answer this. This is the axis about which it's rotating by capital omega. I hope this is called as capital omega. And this is or rotating by this omega. And there's a tension. Basically, why can't I say this? And forget friction. There's no friction because this is purely rolling, right? So mv square by r, and the velocity here is happily equal to omega r. Velocity equal to omega r. There's a force n, and why doesn't this explain the move such a motion? Can someone answer? While it does for a while the same thing does explain the motion for a particle. If this was not a rigid body, it was a particle. I'll give you a minute or so to try because we have less content to cover today. Just 4 questions and all of them easy ones.
I mean, we can take our time because we have Friday also.
Okay, all you need to do is think why this is not working. Where's the fault? What exactly is the fault with this? Okay. See, to be honest, it's gonna take you time because I was stuck with this question for a long time. Okay. In fact, I was stuck with gyroscope for a long time because it's new for me too. Okay. So I was about to give up and say sir to take the tube, but then, okay, I'm doing it somehow. So yeah, just attempt anything. You can be wrong.
V is equal to omega r is wrong.
No, no, this is totally right. I'm taking v is equal to omega r. V is over here. Okay, and this is purely rolling. There's no friction. Okay. Okay, let's say this
Sir,
is not the case. It's not purely rolling. Okay, there's a ground. It doesn't have a friction. Let's just say that.
it's
Now
rolling.
what's wrong with it?
There's no more roll for friction.
Yeah, there's no more role for friction. Okay. Now there's a tension T, mv square by r, n is equals to mg. Everyone is happy with circular motion. We don't need gyroscope. Now what's wrong with this? So, okay, I'll give you the answer. Okay. So basically, in this kind of, if I take this to be true, it does not explain the fact that at a particular time I had an angular momentum in this direction, and after some time I had an angular momentum in this direction. I have nothing in my, math that explains this change in angular momentum. You get that? Basically, if you subtract this L2 by L1, there's nothing in my math. There's no torque. I didn't take any torque. There's no force that's doing it. So basically, I cannot take this. Now you understand that, right? Does anyone have a doubt in this? Basically, the angular momentum due to the wheel is I omega. Okay, so the this is changing. So since it is changing, there's nothing. If I take it this way, the tension and normal, whatever I used to do in my circular motion, there's nothing in my math or nothing in my logic that explains this L1 L2 minus L1. So hence we know for a fact that there's a force being applied by this pivot. Okay, some force over here which has its component F downwards, let's say, and F towards the pivot, and due to that normal is greater than mg, which is causing a torque in this direction. But since it is not since it is spinning, since the disk is spinning, instead of rotating in this way, it rotates in this way. So yeah, that's pretty much it. There's a rolling coin which is tilted by alpha, some alpha. Okay, and basically, you need to find uh, the tilt, the angle alpha, which is causing this coin to rotate in this path. This is the B, radius of the bigger circle, and R is the radius of the coin, and there's some omega s. Okay, or just take that. Okay, omega s, and basically this is rotating in this way. Okay, with omega, so it has some L over here, and it's purely rolling. So same question, it's the same setup. Now you know gyroscope, just like you knew circular motion. Now you know gyroscope. Okay, this is circular motion. This is gyroscopic motion. dl by dt is equals to torque is equals to omega L. Yeah. Okay, so answer me a few questions. Okay, so who is applying the torque here? See, it has an L over here. After some time, it has an L over here. Okay, something is causing this torque to change, right? So who is applying the torque? Who is applying the torque? Also, by the way, if you're confused how this comes, look into section 1.10. Oh, just a second. Yeah, 1.10 or 1.20, I don't remember. Yeah, so you'll know how this comes. It's quite simple.
So we have a rolling coin. Radius is B. No. Which radius is R? The coin of.
So the coin's radius is R, and B is the radius of the movement of the coin. I mean this circle, this one.
Okay. And the path of the
So
coin of radius R. The
is
path.
the
If you look at the
yeah
question, the,
okay.
uh,
I did it according to the diagram, I guess.
okay.
Yeah, so I'll just change it. So this is R. Okay, my device is hanging, and this is B. Okay, so it doesn't matter. It's just okay.
Yeah.
So yeah. So okay, who is causing the torque here? See, you know it's a gyroscopic setup. There needs to be a torque exactly perpendicular to L, which will cause the change in this angular momentum. Okay, fine. I guess I'll proceed. Okay. Is there if I guess there's no other question to ask except for this. Yeah. So basically, there's a force. There's normal force over here. There's mg, and there's a force towards this direction. Okay. So now the force towards this direction is nothing but mv square by r. Obviously, because it's moving in a circle.
And what's
Moving
causing?
in a circle.
Somebody please answer. What is causing this F? That's inward. That's radially inwards towards the center. Where is this force coming from? Could you please answer? Anyone?
It's quite easy, guys. Do you see any strings attached? Anyone pushing it? No, right? So there's only one person who can do this.
It's a coin rolling on the table. Is friction required at all in this problem? Take a guess.
No,
Guys.
sir.
What do you mean? Just a second. There's a car. Okay. It's moving in a circular motion. What's giving the force over here in the radial direction?
Centripetal force.
Friction, sir.
Yeah. But what's caused? That's the name of the centripetal force. But what's causing in a string? It's tension.
Friction.
Yeah, exactly. So what must be causing it over here?
Friction, sir.
Yeah, exactly. Friction. So this is a torque equation. Friction R, cos alpha. Okay, minus nr sine alpha. Okay, and this is the equation for gyroscope. Dl by dt is equal to torque is equals to omega L cos alpha. Now just see the fact that there's an extra cos alpha because the torque will cause it to change only in this direction. Because if you see the torque which is being acting, it's r cross f. Okay, so r cross f will give you a direction which is perpendicular to this line, not this line. So there's a cos alpha over here,
So the coin is
and
leaning.
this is
So the coin is leaning at an angle alpha, and you'll see that once this coin keeps rolling, the vertical direction angular momentum is not going to change, but the horizontal component will change. That's why it depends on this cos alpha. Can you see that? Why do I say that? The vertical component is going to remain as it is, which is L sine alpha, pointing downwards, but only the horizontal component is going to change as this coin keeps rolling. Would you agree?
because it will slow down, right? Eventually the coin, so it has to be changing. Like if there was no air resistance, I don't think this would change, right? And in a very ideal case, but that's not the case because even a slight tilt can cause it to change. So in a very ideal case, yeah, I don't think it would change, right, sir?
Which one? Can you please repeat?
Yeah, if in a very ideal case, I don't think this would change, right? Where there's no air and
Right, right. It,
there's
it, it will continue the same way. The friction is there, but it won't do any work. So it will continue going in that circle forever.
okay. Now you know gyroscope, the traditional gyroscope, S- just like circular motion. You know, the first time you encountered circular motion, it was a mass, it was a string. Okay. Now you don't need the string. You have many equivalents of that. There's road, there's car, there's friction that's causing a circular motion. Or let's say there's earth, there's a satellite, the gravity is causing the circular motion. Similarly, these are equivalent, systems. So similarly here, you don't need the axis. Okay, you have this. Now you can see this is rotating by omega, which is similar to this. It's a very equivalent system. And here the tension is providing the torque. There's no gravity. I have turned off gravity. Okay, I have turned off gravity. No, this is too well. Okay. So basically, tell me what do I need to do in this? We are doing it from 3 questions. Okay. Now tell me what I need to. Just tell me the equation, if someone can. We did it 3 times, guys. This is the fourth question. This is for circular. What should be for gyroscope? Okay, fine. dl by dt is equals to torque.
Sir,
Okay.
omega L.
Yeah. Right. Exactly. Omega L. Or I guess 2L over here. No, L. Yeah. It's omega L. So that's it. Basically, you need to. This is just a some super fancy question which requires us to write the torque in a super fancy way, and that's it. You just need to equate. So there's some it will tilt like this. Okay. It says there's a very tiny tilt. Basically, the beta is very small, very small. Like you cannot imagine that small. Okay. So due to that, there's a force over here. So R cross T, due to the tension that's providing the torque. Okay, which is causing it to rotate in this direction. Okay, so basically this is beta. If I take this is parallel, this is our okay. Hello, can you hear me? Hello.
Yes, sir.
You can hear.
Yeah, yeah. So beta is this. Okay, this is your coin or whatever disk you call. Okay, it tilted a bit beta by this. So basically this will be 2 beta. Okay, and so basically if you apply T at point A is this is point B. So there are 2 torques. One is this L cross. So basically the component of this is L. Okay, this is L, and the component of tension which is in this direction along along this would be T sine 2 beta. This is beta, so this is 90 degree. So along this direction, along the green arrow, it will be T sine 2 beta. So your torque is LT 2 beta because sine x for very small angles of x is equal to x. Similarly, here torque at B would be this. Now if you see both the torques are in same direction, so total torque is 4T LB. Now again you apply this. That's it. Solved. You had to solve for beta. See how simple that is. Okay. So, so I guess I'm done with today's tute, but I still have time left. Okay. So I will revise. I will try to give you, again some insights on gyroscope. Okay, there's a torque. First, it was acting in this. It is spinning. Okay, it's a torque. It was acting in this direction. At this moment, when the wheel was over here, the torque is acting, in this direction. Then when the wheel is over here, the torque is acting in this direction. So basically, if I for t by 4 time period, if I take average torque, which would be here, this would cause the angular momentum to reduce in this direction and gain in this direction. So similar to circular motion. Okay, again.